Hello students, welcome to my class Astrophysics. Today we will learn about the interference of light, and for that we have to know about the coherent and incoherent sources of light. And first of all, when we want to study the interference of light, it is the phenomena of superposition of two light waves. So we have to know about the principle of superposition of waves. When a number of waves traveling through a medium superimpose on each other, the resultant displacement at any point at a given instant is equal to vector sum of the displacement due to individual waves at that point. And if y1, y2, y3, yn, there are n number of waves, they come and meet at the same point at the same time. And these are their displacement at that moment, at that place, due to their different waves acting separately. Then according to the principle of superposition, the resultant displacement when all the waves act together is given by the vector sum of. That means these are the different displacement of the different waves, they traveling through the same medium at the same time. They meet at a particular point. Obviously, there will be a resultant displacement, and according to this superposition principle, the resultant displacement, if we write mathematically, that is the y vector, that is the y1 vector plus y2 vector plus y3 vector and plus up to yn vector. When the two superposing waves are in the same phase, that is the crest of one falls over the crest of another, or the trough of one falls over the trough of another, that displacement get added. When the two waves meet in opposite phases, that is the crest of one wave falls over the trough of another, that displacement get subtracted. Here in this figure diagram, there are two waves, first wave and second waves. They meet at a particular point, particular place in the same phase. In the same phase means here at the same time the crest superimpose with the crest and the trough on the trough. Practically they are moving along the same point, same directions. But here to draw it, we take separate places, but they are moving along the same line, and they superimpose with each other with the same phase, that with crest and trough with trough. Naturally, that the direction of the displacement of the two waves at any point is same, and therefore their displacement will be added. Their amplitude will be added in this case. In the first figure diagram, it gives the idea about the resultant wave when two waves superimpose at the same phase at the same point. In the second figure diagram, this one, the first wave and second wave, they meet at the point in opposite phase. Opposite phase means the crest with the trough and trough with the crest of the second waves. As a result, the resultant wave will be this type of. That means the resultant amplitude or displacement that will be get subtracted to each other. And it is the superposition principle. So what is the superposition principle? If we say again, it is nothing but the sum of the all displacement of the all waves, they meet at a point at the same time. Here it is to be noted, when a number of waves travel through a medium simultaneously, each wave travels independently of the others. That is, as if all other waves were absent. We get resultant wave at a particular point due to the superpositions, but it does not indicate the resultant waves, that is one permanent effect. When they meet at the same phase at a particular point, at that point we get a resultant. But when these waves cross that point, they travels as such a manner that there are no other waves and there are no meeting with the other waves in the path between them or in them. Now our topic is interference of light. What is the meaning of the interference of light? First of all, we have to know it. When two light waves of the same frequency and having zero or constant phase difference, same frequency means same color or same wavelength, and there is one important term, that is the constant phase difference, traveling in the same direction, superpose each other. The intensity in the region of superposition get redistributed, becoming maxima at some points and minimum at other points. This phenomena is called interference of light. That means simply interference means redistribution of light energy due to the resultant effect of two superposing waves at a particular point. And the condition is the wave of same frequency or wavelength, number one, they're moving along the same direction, number two, and there must be a constant phase difference at a particular point when they meet with respect to time. There should not be change in the phase difference. There are two types of interference taken place simultaneously at the same places. Number one, constructive interference, when the two superposing waves are in the same phase. The amplitude of the two waves get added up and hence intensity I varieties a square becomes maximum. This is called constructive interference. That means when two waves meet at a particular point at the same phase, naturally their amplitude get added, and since amplitude increases, the intensity also increases. And we know the intensity of the light waves, not only light waves, for any waves, intensity that depends upon the amplitude. Intensity that directly proportional to the amplitude square. When amplitude increases, naturally at that point, intensity increases due to the superposition of the two waves. At that place, we can say brightest spot of light. And this is known as the constructive interference. Constructive interference means the intensity maximum. At the same time, just a neighbor of this constructive interference, there will be destructive interference also. When the two waves meet in opposite phases, the amplitude of the two waves get subtracted and hence the intensity becomes minimum. This is called destructive interference. That means at the same medium, there will also be destructive interference when the two waves or where the two waves meet at opposite phase, their resultant of amplitude decreases. Since amplitude decreases, therefore intensity decreases, and we get a minimum intensity at that point. That place is known as the destructive interference. Both constructive interference and destructive interference taken place all together. Here we can see one interference pattern here. The constructive, this point is the constructive interference, and this dash break is the destructive interference. Practically, where constructive interference taken place, the brightness is increases above the normal brightness, and the dark point, that will be the brightness of that these places, decreases up to minimum, maybe completely dark. It is due to the redistribution of light energy. There is no creation or destruction of the light energy due to the interference. Only there are redistribution of the light energy. Here there are two interference patterns. And the first one in red monochromatic light of red color, and second is the yellow color. This type of interference pattern we obtain when two light superimpose and constructive or destructive interference taken place. This place, it is known as the constructive place, and this neighboring place, it is the destructive place. So this phenomena is known as the interference of light. Now, what are the required conditions for constructive and destructive interference? Expression for intensity at any point in interference pattern. To find out the conditions, first of all, we have to calculate what is the expression for the intensity of light at any point due to the superposition of the two or interference of the two light waves. Let us suppose the displacement of two light waves from two coherent sources S1 and S2. At last, we will learn about the coherent sources. What is the meaning of the coherent sources? Now just know you when light coming from two coherent sources S1 and S2 at point P, at any point on the screen or place where we have to observe it. On the observation screen at any time T, we consider the displacement of the first wave, the equation for it, y1 is equal to a1 sine of omega t, and y2 that is equal to a2 sine of omega t plus phi. Here y1 and y2, these are the two displacement at that moment at that time t. a1 and a2, their amplitudes. These may be same or nearer to same. But omega same, that means frequency must be same, otherwise you cannot observe this interference pattern. And there is a, let us suppose phi is the phase difference, and that phase difference sustained with respect to time, that means that will be constant with respect to time. So there are two waves on the screen, and let us suppose the screen that is placed at x is equal to 0. Therefore we can write this type of equation. There is no x term here. Practically these are the equation of the oscillations, but here if we take the screen, the point P that is at a plane which passing through the origin, that is x is the 0, then we can consider this type of equation. Now there are two waves, y1 is equal to a1 sine of omega t and y2 is equal to a2 sine of omega t plus phi, where a1 a2 are the amplitudes of the two waves, phi is the constant phase difference between the two waves. By superposition principle, the resultant displacement at point P, that will be y equal to y1 plus y2, that is a1 sine of omega t, and y2 equal to a2 sine of omega t plus phi. By calculation it, a1 sine of omega t and a2 sine of omega t into cos of phi plus a2 into sine of phi into cos of omega t, which is equal to y equal to a1 plus a2 cos of phi by taking the common sine of omega t here, a1 plus a2 cos of phi into sine of omega t plus a2 phi whole into cos of omega t. Now let us suppose this term, it is equal to capital A cos of theta, a1 plus a2 cos of phi, let us suppose that is a cos of theta, and a2 sine of phi, let us suppose that is a sine of theta. Let us consider, and after that we have find out what is the a, what is the theta. You can find out with the help of these two equations. Now what's happened, y equal to a cos of theta into sine of omega t from this equation and these two equations, plus a sine theta, we have taken a2 sine of phi, the a sine theta, capital A sine theta, into cos of omega t. And from that we get y equal to a sine of omega t plus theta. That means it is nothing but the resultant wave after the superposition the two waves, and two waves where y1 a1 sine of omega t plus y2 equal to a2 sine of omega t plus phi, phi is the phase difference. We get a resultant of equations that is also a wave equations. The resultant wave is also a harmonic wave whose amplitude is a, and it leads the first harmonic wave by phase angle theta. That means the resultant wave whose amplitude is the capital A and leads by angle theta leads with the first wave, that means a1 sine of omega t plus theta. The theta is the angle, phase angle that leads first harmonic waves by phase angle theta. Now we are interested about the resultant amplitude A, because the intensity of sound, that sound, not sound here, it is the light for the all waves, not only sound, not only lights. The intensity that depends upon the amplitude of the waves. Now we are interested about the resultant wave. That means what will be the value of the A. We can get the value of the A with the help of these two equations. If we add after the squaring these equation 4 and 5. That means to determine a squaring and adding the equation 4 and 5, we get a square cos square theta, and in the right hand side a1 plus a2 cos of phi whole square plus a square sin square theta, that means plus a2 sin phi whole square. In the left hand side, if you take the common a square, the square whole into cos square theta plus sin square theta, that is 1. Therefore, a square is equal to a1 square plus 2a1 a2 cos of phi plus a2 square, and if we take the common, here a2 square cos square phi plus a2 square sin square phi. If we take the a2 square common, the cos square phi and sin square phi, that is nothing but the 1. That means a square that will be a1 square plus a2 square plus 2a1 a2 cos of phi. Therefore, a will be root over a1 square plus a2 square plus 2a1 a2 cos of phi. What is the phi? I am telling again. It is the phase difference between the two superposing waves. Phi. It is just like the equation of a vector resultant. R is equal to root over p square plus q square plus 2pq cos of theta, where theta is the angle between the two vectors a and b. Therefore, we can easily remember it. A square resultant amplitude square, that is the a1 square plus a2 square plus 2a1 a2 cos of phi. But intensity of a wave, that's directly proportional to the amplitude square. We know it. It is not only the light waves, for any waves, any electromagnetic waves. Obviously, also for the mobile signals, we are openly saying the strength of the signal is very less. So what is less? The amplitude is less. If we improve the amplitude, then we can get the more intensity. Now, for the light intensity of a wave, that is very amplitude square. Therefore, we can write I is the resultant intensity after the superposition. That is very a square, that means k into a square. I1, that is k into a1 square. I2, that is k into a2 square, where k is proportionality constant. So in this equation, if we multiply both sides by the k, then we can write k square equal to k a1 square plus k into a2 square plus 2 into root over k1 into root over k2 cos of phi. Root over k and root over k into root over k, that means k. We multiply both sides of this equation by the k, that is proportional constant. And now we can write it is nothing but the I equal to I1 plus I2 plus 2 into I1 into I2 root over cos of phi. This term is known as the interference term in this equation. This equation gives the total intensity at a point where the phase difference is phi. Total intensity means after the superposing of the two waves, where theta is the phase difference between the two waves. And which type of waves? Now they have the same frequency, same wavelength, and they are moving in the same directions. At a particular place, they meet with a phase difference phi. Here, I1 and I2 are the intensities which the two individual sources produce on their own. Total intensity also contain a third term, that is 2 root over I1 I2 into cos of phi. It is called the interference term. Why it is so called? If interference is not taken place, let us suppose two lights coming from the two sources and their intensity I1 and I2, and they incident on a particular screen. Normally we think the intensity will be added, and that is a normal phenomenon, and that intensity should be I1 plus I2. But here, after the superposition, we get another third term here. Rather than I1 plus I2, we get I1 plus I2 plus 2 root over I1 I2 cos of phi. Now, this is extra term, and it is known as the interference term. So what will be the resultant intensity I? That now depends upon this term, and it is known as the interference term. If interference not taken place, then this term will be 0, and the intensity will be the sum of, ordinarily sum of I1 plus I2, which is observed in our daily life. When I1 is equal to I2 is equal to I0, let us suppose. Let us suppose the intensity of the two waves same when they superpose each other. Then the equations, this equation becomes this is I1 and I2, I that is equal to I0. And what will be the resultant intensity? That is I is equal to I0 plus I0 plus 2 into 2 over I0 into I0 into cos of phi. And it is 2 I0 plus I0, 2 I0 plus 2 into I0 square. That is also the I0 and a cos of phi. Then if we take the common 2 I0 all into 1 plus cos of phi. So resultant intensity, if the two waves of the same intensity, then that will be 2 I0 1 plus cos of phi. And this cos of phi can be written 2 into cos of phi by 2. That means 1 plus cos of 2 alpha. That is the 2 cos per alpha. If we consider phi by 2 as alpha, then from this we can write 2 I0 into 2 cos per phi by 2. That means resultant intensity in this special case, when the intensity of the two incident waves are same, that will be after the interference 4 I0 cos per phi by 2. That means at any point, it is not so always that waves meet at a particular point in the same phase, or opposite phase means phase difference 180 degree, that means pi phase difference. They may also meet with a different phase angle difference. Therefore, in such a case, we can easily find out what will be the intensity at that point with the help of these equations by only putting the value of the phi, that is the phase difference of the two waves they meet at that point. Now, what will be the different unit in SI systems? Obviously, A1, A2, or A, all these are measured in meter, and I1, I2 in I3 or I, all these in watt per meter square. Practically, it is a unit of all types of intensity of waves, light waves, sound waves. Watt per meter square means joule per second per meter square. That means at any point, what is the intensity of any waves, not only the light waves. That is, what is the energy, joule, passing through a unit area per unit time, joule per second per meter square at that point. And if you take the area, that is perpendicular to the directions. Therefore, unit of I1, I2, and I, that will be always watt per meter square. Now, we have the expression for the resultant intensity after the interference. And it is when interference taken place at the different places, this expression equally valid for the constructive interference, destructive interference. And what are the now different conditions that can be obtained with the help of this equation? The resultant intensity at the point P will be maximum, because here we see it is the interference term. When this term is the maximum, at that time resultant intensity will be maximum. And I1, I2, these are constant. If interference taken place or not, there will be no change of the I1, I2. That is the individual intensity of incident waves. Now, I depends upon the cos of phi. What is the maximum value of the cos of phi? That is the 1. And minimum value, that is the -1. When cos of phi will be 1, at that time we get maximum intensity I. And according to our definition, that is the condition for the constructive interference, where we get the maximum intensity. At that place, we are saying the constructive interference is taken place. The condition for constructive interference, the resultant intensity at the point P will be maximum when cos of phi is the 1. And when the value of the cos of phi is 1, now when phi 0 degree, 0 or 2 pi or 4 pi or 6 pi, that means when the phase difference of 2 pi corresponding to path difference lambda. Therefore, if P is the path difference between the two superopposing waves, then from the relations, phi is the 2 pi by lambda into P. Now, what is the fact about this? Now, we have now conditions about the phase difference. Two waves are coming from the two sources, and they meet at a point. And at that point, if there is a constant phase difference, either 0 or 2 pi or 4 pi or integral multiple of the 2 pi or even multiple of the pi, at that places we get cos of phi the 1. That means intensity will be maximum, and we are saying at these points constructive interference taken place. But why these phase difference taken place? Let us suppose waves coming from the two sources. Initially, the two waves they have the same phase, but when they travel distance, they meet at different points on the screen. There may be a path difference, and due to the path difference, there will be a phase difference. Now, what is the relationship between the path difference and phase difference of any waves? The path difference, if it is written by the p, maybe x or p, and phi the phase difference, then relationship between the path difference and phase difference, the phase difference pi is the 2 pi by lambda into p. We can get it for the when we consider the path difference is the lambda, that means wavelength, then there is a phase difference 2 pi. That means the two successive same phase point, they are separated by a distance lambda, and successive same phase point means there is a phase difference 2 pi, next 4 pi, next 6 pi, etc. So distance between the two successive same phase point, that is lambda, and these are same phase point means exactly phase, not same phase, there is a phase difference 2 pi. So for the lambda, phase difference 2 pi. Therefore, for the p, phase difference 2 pi by lambda into p, and that is phi. That is the relationship between the phase difference and path difference, and this relationship is very important. We will use it several times. The phi, the 2 pi by lambda into phase difference. That means either we can get the condition from the phase difference. Also, we can obtain the condition from the path difference. How can we obtain? Now, in this case, pi is the, for the constructive interference, pi the 0, 2 pi, 4 pi. That means 2 pi by lambda into p. That is the path difference is the 0, 2 pi, 4 pi. Or p is equal to, if we multiply it in these equations, then p is equal to either 0 or lambda or 2 lambda or 3 lambda or n lambda. Hence, the resultant intensity at a point is maximum when the phase difference between the two superposing waves is 0, or an even multiple of pi, or integral multiple of the 2 pi, or path difference is an integral multiple of the wavelength lambda. This is the condition for constructive interference. When we will deal about the Young's double slit experiment, at that time we will use this condition, either phase difference 0, 2 pi, 4 pi, 6 pi, etc. or path difference, that is the 0, lambda, 2 lambda, 3 lambda, and these two waves meet at a point, and with respect to time there is no change in this phase difference, then we get the constructive interference at that point. That means we get the bright light spot at that point. For the destructive interference, that means what are the different conditions for the destructive interference? Again, if we consider the resultant intensity, this term, the resultant intensity depends upon this term. That means specifically the cos of phi, and the minimum value of the cos of phi is the -1. At that time, what will be the I? That I will be cos of phi minimum, and cos of phi the -1. For what values of phi, the cos of phi will be -1. Now phi, the pi, 3 pi, 5 pi, that means odd multiple of the pi, then cos of phi will be -1. And this is the condition according to phase difference. And again, we know 2 pi by lambda into path difference is the phase difference. For the destructive interference, that means where we get the minimum, the values of phi will be pi, 3 pi, 5 pi, etc. From that, we get the condition for the path difference. Now, two waves coming from the two sources, initially they have same phase, and they meet at a point. And at that point, if their path difference, that will be either lambda by 2 or 3 lambda by 2 or 5 lambda by 2. In general, if we write 2n plus 1 into lambda by 2, where n is the 0, 1, 2, 3, etc. At that places we get the destructive interference. Hence, the resultant intensity at a point is minimum when the phase difference between the two superposing waves is an odd multiple of pi, or the path difference is an odd multiple of pi lambda by 2. This is the condition for destructive interference. These two conditions we will use when we calculate the fringe width in ion double slit experiment or in other cases. Interference taken place any place. These are the conditions, either according to phase difference or according to path difference. And when we consider the path difference, if they emit from the same wavefront, that means initially waves have the same phase, and due to their different path traveled before the meeting at point P, there will be a path difference. Then we can use this type of formula of the dependency of the path difference. Otherwise, the phase difference, it is in general everywhere you can apply the phase difference conditions to get the constructive interference pattern and destructive interference patterns. Now it is to be noted, from the above discussion, we find that interference is constructive when cos of phi is 1. Then what will be the A? That means what will be the resultant amplitude at the constructive interference point? And that will be root over a1 square plus a2 square plus 2 a1 a2 cos of phi. And now condition is for the constructive cos of phi the 1. Therefore, a will be root over a1 square plus a2 square plus 2 a1 a2. That means root over a1 plus a2 whole square. That means a1 plus a2. That means where the constructive interference taken place, the resultant amplitude will be the sum of two individual amplitude of the two superposing waves. And at that place, the resultant amplitude also be maximum. And the value of the maximum, a max, that is the a1 plus a2, that is sum of the amplitude of the two waves. Obviously, I max, that will be k into a1 plus a2 whole square, because I max or any intensity that depends upon the square of the amplitude. So I max, that is proportional to the a max square, or I max proportional to a1 plus a2 whole square. Again, interference is destructive for the what will be the resultant amplitude. When cos of phi, that is equal to -1, and we get a is equal to root over a1 square plus a2 square plus 2 a1 a2 into -1. That means it is root over a1 minus a2 whole square. Therefore, a will be a1 minus a2. That is the difference of the amplitude of the two waves, which would be minimum. That means minimum for destructive interference taken place, where the a minimum resultant amplitude, that will be a1 minus a2, that is the difference of the two amplitudes. And at the maximum place, that means at the constructive interference, resultant amplitude will be the sum of the two amplitudes. Naturally, the intensity also decreases at that point, and the I minimum, that is the varieties a minimum square, therefore I minimum varieties a1 minus a2 whole square, or I minimum, that is the k into a1 minus a2 whole square. And if you want to find out the I max by I minimum, that will be a1 plus a2 whole square divided by a1 minus a2 whole square. From this, you can find out the ratio of the I max and I minimum. When a1, a2 is the a, let us suppose the amplitude of the two waves superpose at a point same, and that is, let us suppose small a1, a2 equal to a2 is the a. Therefore, a max will be 2a, and I max, that will be k into 4a square. And what will be the a minimum? That is the 0. I minimum also 0. That is, dark fringe will be perfectly dark, and the contrast between bright and interference, dark interference fringes will be best. That means when the intensity that depends on the amplitude of the two waves, they are coming and meeting at that point same, the resultant at the minimum place, at the destructive interference place, the resultant amplitude will be 0. Therefore, I minimum will be 0. That means we get completely dark positions, and we can clearly see the interference pattern dark and bright, and there will be good contrast. Otherwise, if there is a variations, that means a1, a2, the difference is not so small. There will be a variations of the intensities, bright and relative bright, but not completely dark. Therefore, to get a good contrast, we should have the amplitude of the two waves same, and it is obtained in ion double slit experiment. Now, Young double slit experiment, that means intensity depends upon the slits. Slits means linear holes, slit widths. If W1 and W2 are widths of two slits from which intensity is applied I1, I2 emanate, then W1 by W2, that is proportional to the intensity I1 by I2, that will be A1 square divided by A2 square. That means I intensity which intensity of light which emanates through a slit, that proportional to the width of the slit. That means if the width of the slit is more, the intensity of light coming through that slit will be more. This concept is also, it will be used to solve different questions. Now we going to another topics, that is coherent and incoherent sources. When we define the interference pattern, at that time we have stated that the light coming from two coherent sources, then interference pattern is taken place. Otherwise, if light coming from the two incoherent sources, you cannot observe interference on the screen. So let us first, we have to know what do you mean by coherent sources and incoherent sources. Coherent sources, two sources of light which continuously emit light, same frequency or same wavelength, with zero or constant phase difference between them, are called coherent sources. To be noted some points: continuously emit lights, number 1 point; same frequency and same wavelength, number 2 point; with zero or constant phase difference, number 3 point, are called coherent sources. Here, most important point is with zero or constant phase difference. Incoherent sources, the two sources of light which do not emit light waves with a constant phase difference, are called incoherent sources. That means even if the light coming from the two sources, they have the same frequency or wavelength and continuously emit light also, but if there is no constant phase relationship between the two waves, that means there is always variations of the phi, then we cannot observe the interference pattern. And in such a case, these two sources will be known as incoherent sources of light. Need of coherent sources for the production of interference of pattern. Why we require the coherent sources? Otherwise, we cannot observe the interference pattern. And why in our daily life we several times observe the light coming from the two different sources, even if they are in the same, they are of same color, but we cannot get on the interference on the screen. Why? When two monochromatic means single color, single frequency, wave of intensity I1 and I2, phase difference phi, meet at a point, the resultant intensity is given by this. Already we have calculated it. Resultant intensity I will be I1 plus I2 plus 2 into I1 I2 cos of phi. This term 2 into I1 I2 cos of phi is called the interference term. Now there are two possibilities. If the cos of phi remains constant with time, number 1, and if cos of phi varies continuously with time, then what will happen? If cos of phi remains constant with time, the total intensity at any point will be constant. The intensity will be maximum root over I1 plus root over I2 whole square. When cos of phi is 1, this one. And points which cos of phi is a plus 1. And the minimum, that will be root over I1 minus root over I2 square, we can get from this formula. If we put here cos of phi is minus 1, then the equation will be I is equal to I1 plus I2 minus 2 and I1 root over I1 I2, and that will gives you the result root over I1 minus root over I2 whole square at points where cos of phi is minus 1. The sources in this case are coherent sources because there will be no change, constant. For a particular point where we get maximum, always we get maximum. And for particular places we get minimum, always we get minimum. If cos of phi varies continuously with time, assuming both positive and negative values, then the average value of cos of phi will be 0 over the time interval of measurement. If there is a variations continuously, then what will be the average value of the cos of phi? If phi varies continuously, now negative value plus positive value, and ultimately the average value will be 0. Therefore, this term will be 0. The interference term will be 0. Therefore, we get equal illumination on the screen, and that will be equal to I is equal to I1 plus I2. To understand these points, one thing should be clear. Light coming from the two different sources, they meet at a point. And suppose we get the interference constructive one, but that momentarily, and the light which is coming behind, or with respect to time, the light is coming, then we can get this type of, or we can see anything when light is continuously coming from the source. It is not so one interference taken place and you see for the whole day, or it is not so that one your book that is exposed on the light and then after that you can read it throughout the whole night without any source of light. It is not so. You can get light when light coming continuously from the source. Light incident at that point. Next moment, another waves are also coming. They are incident at the point. Next waves coming. They are incident at the point. And if there is a constant phase difference, all the incoming light waves from the two different sources at that point, then we can get the interference pattern. And in later on, in case when the later on light waves coming at that point, they meet at a different phases and there is a continuous variation of the phase. So we cannot observe this. That means when cos of phi, that will be 0 and we get equal illuminations. Then the interference term averaged to 0, there will be same intensity at each and every point, and that will be I is equal to I1 plus I2 at every point, which is generally normally observed in our daily life. There will be general illuminations on the observation screen. The two sources in this case are incoherent. Hence, to observe interference, we need to have source with same frequency with a stable phase difference. Obviously, continuous light. They are coming from the two sources continuously. Otherwise, you cannot see any observe. We cannot see anything. Light should come continuously from the two sources of the same frequency, and there must be a stable phase difference. Then we can get a sustained type interference. Such a pair of sources are known as the coherent sources. Otherwise, if there is always variation of the phase difference, all other conditions satisfied, but phase difference continuously varies, then we cannot observe the interference pattern. And in such a case, since their frequency is same, wavelength same, and but there will be no interference pattern, these will be no the coherent sources. So coherent sources means wavelength we need two sources of light, same frequency and with a stable phase difference continuously coming from the two sources. Now one question is, two independent sources cannot be coherent. It is a statement. Why two independent sources? Maybe they have the same monochromatic, they emit same monochromatic light, both emit suppose yellow lights or red lights of single frequency, but the sources are different sources. So why two independent sources cannot be coherent? This is because of the following reasons. Number one, light is emitted by individual atoms and not by the bulk of matter acting on as a whole. And when we read how light is emitted from a source, practically light emitted by individual atoms and molecules, not as a whole the matter or as a whole the object. As for example, light coming from the sun and light emitted by the different atoms or ions or molecules, but not as a whole the sun. And what is the mechanism of the emission of the electromagnetic waves or light? Now, it is due to the energy transition from the excited state to ground state. Even a number point 2, even a tiniest force consists of millions of atoms, and emission of light by them takes place independently. All atoms, they emit lights independently, not influenced by other atoms near about it. All these atoms, they emit light independently. And what is the source of that light or electromagnetic waves? Even an atom emits an unbroken waves of about 10 to the minus 8 seconds due to its transition from a higher energy state to lower energy state. And you know it, when the atoms or molecules emit light, before that it will have to pass to excited state by absorbing some energy. And then this excited state, that is unstable state, and it has to emit some energy in the form of electromagnetic waves that transition from the higher energy state to lower energy state. And this time taken for it about 10 to the minus 8 to 10 to the minus 9 seconds. That means during that, one atom emits light. An atom emits an unbroken waves about 10 to the minus 8 second to 10 to the minus 9 second due to the transition from this. That means what is the time taken to transit energy levels from higher energy level to lower energy level. During that time, it emits energy in the form of electric waves. Therefore, an atom emits an unbroken wave of about 10 to the minus 8 seconds. The millions of atoms of a source cannot emit wave in the same phase, because all the atoms, they emit waves independently. The light emits by the commonly used monochromatic source remains coherent for about 10 to the power minus 8 seconds. After this time, the atoms responsible for the emission of light get changed. Light coming from a particular source, and that is made up of millions of atoms, molecules, and they emits, not all the atoms, always some atoms or molecules, they emit electromagnetic waves or light waves. But the time of emission of light waves by a single atoms, that is about 10 to the minus 8 seconds. Next, light waves emitted by other atoms. The atoms responsible for the emission of light get changed. Next, another atoms, they will emit light. We get continuous light because so many atoms there simultaneously emitted light one after another. The phase difference and hence the interference pattern changes 10 to the power 8 times in 1 second. That means if light coming from the two different atoms, they will be coherent for only 10 to the power 8 times in 1 second. And therefore interference pattern taken place 10 to the power 8 times per second. Our eye cannot see such rapid changes, and a uniform illumination we get. It is seen on the screen, and uniform illumination is seen on the screen. So two independent light sources cannot produce a sustained interference. Then how can we get the interference pattern? How can we make the two coherent sources? Now, what are the conditions to obtain the two coherent sources? Number one, two sources of light must be obtained from the single source by some method. It is one way. Then the relative phase difference between the two light waves from the source will remain constant with time. That means we have to take two sources of light from the single source by some method. Number two, the two sources must give monochromatic light. Monochromatic means single color, single frequency, single wavelength. Otherwise, different colors will produce different interference patterns, and fringes of different colors will overlap. If a not monochromatic light, then different colors, they will produce different interference pattern, and they will overlap, and we cannot get separate interference pattern. That means we cannot understand interference pattern is taken place or observe interference pattern taken place or not. Number three, the path difference between the waves arriving on the screen from the two sources must not be large, because path difference, it is more than the 30 centimeter. That means what is the light travels in 10 to the minus 8 second to 10 to the minus 9 second. The path difference not should be more than that, and that is around 30 centimeter to 3 meters, let us suppose. It should not exceed, now it is better that it should not exceed 30 centimeter. then the phase difference produced due to the path difference will not be constant. There will be general illumination on the screen. These are the different conditions. How can we obtain coherent sources? Number one, we have to take two light from the same source by some method. The two lights coming from that must be monochromatic. That means they must have the same frequency, same wavelength, and path difference that not should be so large. That means it should not be exceed more than 30 centimeter. Now, question is how can we obtain the from a single source? And there are several methods in our syllabus, standard 12 CBSE. We have to read about the Young double slit experiment, and that will be our next lesson. Young double slit experiment, the two sources S1, S2 get light from the same source S. Whatever phase difference or phase changes occur in the S1, the same phase changes occur in S2. The relative phase difference between S1 and S2 remains constant with time, so they act as coherent sources. That means when we will study the Young double slit experiment, it will be clear. In Young double slit experiment, we take the two sources from the same wavefront. From the same wavefront, S1, S2, we consider, and therefore always S1, S2 initially at the same phase. And if there is a change, simultaneously there will be change in the S1, S2 also. So when initially they emit from the two slits S1, S2, they will be at the same phase always, and therefore there will be a constant phase difference with respect to time. And consider coherent sources. Another two experiment also, these are not in your syllabus. Fresnel biprism, Loard's mirror. In all cases, two coherent sources are obtained from the same source, same parent source by the reflection method or by reflection method, and so on. And in our next lesson, we will learn about the Young double slit experiment, and we will find out the fringe width.